This is what we call a motion problem, and it's going to use the formula rate times time equals distance. So in this problem, we have two private airplanes traveling toward each other from cities that are 780 kilometers apart. It's sometimes helpful to just do a little sketch so you know what's going on, because that's going to help you with what you want to do with the distances. So here we have one city, and then we go over here to the next city, and we know the distance between these is 780 kilometers. And we have two airplanes traveling toward each other. So one is going to be traveling this way, the other is going to be traveling this way, and they're going to meet somewhere in here. What we know when they meet is their combined distances is going to be that 780 kilometers, so that's probably going to be helpful. To set up equations, and in this chapter we're using two equations because it's systems of equations, you could actually solve these problems with one equation, but we're going to go ahead and use two variables. It's often helpful to organize your information in a little table. So we have, we'll just call it plane 1 and plane 2. And they've given us the rates. One of them is traveling at 190, and our units are kilometers per hour on rate, so our time is going to be measured in hours, and our distance is going to be measured in kilometers. And the other one is traveling at 200 kilometers per hour. They leave at the same time, so in how many hours will they meet? Well, I don't know how many hours they actually travel, but I do know that it's the same, so I can use T to represent the hours that plane 1 traveled and also the hours that plane 2 traveled. I don't need two different variables because that's going to be the same number. Now their distances, and I'm using two equations so I can use two variables. If I let the first distance be represented by D, and I go back over here to where I thought about what was happening in the problem, and the sum of the distance is 780, well, if this one goes D, the other one must go 780 minus D. And then I've written my formula on top of my box, my table, and it tells me what to do with the items in the individual cells. So rate times time equals distance for the first plane would give me 190 times T equals D. And for the second plane, 200 times T equals 780. This is a natural substitution problem since the first equation gives you that D is equal to 190T. So we can solve that by saying 200T is equal to 780 minus 190T. And if we add 190T to both sides, then we're going to get 390T is equal to 780, and that tells us that T is equal to 2 hours. So both planes flew 2 hours, and then they met. Hopefully they were at different altitudes so they didn't run into each other. Okay, the next problem we're going to look at involves a train that leaves Union Station for Central Station. So if I have Union Station here and Central Station here, then I have a train that's going to leave traveling this direction. And again, they give us the distance between is 216 kilometers. And the time is a little bit different here. At 9 a.m. that first train leaves, and then 1 hour later the next train leaves, but going from Central to Union. So it's similar to the problem we just worked in that we've got two vehicles heading toward each other. So we know the sum of the distances they travel is going to be the total distance between the two entities where they leave, which in this problem is 216. So again, we're using the rate times time equals distance formula. And we have train 1, we'll just call it T1, and train 2. And this box just helps us organize the information we have. Okay, so what do I know? Train 1 leaves at 9 a.m. Train 2 leaves an hour later, and they meet at noon. So that means train 1 traveled a total of 3 hours and train 2 traveled a total of 2 hours, from 9 to 12 and from 10 to 12 because it left an hour later. And I don't know the rate of either one of them, and we don't know that those rates were the same, so we need two different variables. We'll let x be the rate of train 1 and y be the rate of train 2. And since I've already got two variables in there, I don't want to introduce a third variable. So I'm just going to make a note here that the sum of the distances is equal to 216. So from this box, I can get the equation 3x, which represents the distance that train 1 traveled, plus 2y, which represents the distance that train 2 traveled, is equal to 216. Now I have more information up here that I haven't used because it gives me a different scenario. It says if the second train started at 9 and the first train started at 10:30, then they'd still meet at noon. Find the speed of each train. So let's make a box that represents that information. So train 1, and it's still going to be traveling at x rate of speed, and train 2 is still going to be y. But this time it says if the second train, train 2, had started at 9 and train 1 at 10:30, they still would have met at noon. So this time, if it started at 9, train 2 would be on the tracks for 3 hours. And the first train started at 10:30 would be traveling a total of an hour and a half. And again, the distances, if I add them together, will be 216 kilometers. So I'm going to get a second equation here. 1.5x, which is rate times time for the first train, so that gives me the distance the first train traveled, plus 3y, rate times time for the second train, and that has to equal 216. So now I've got two equations in two variables, and I should be able to solve those. This is a good problem for elimination because if I multiply this equation by 2, I'll get 3x plus 6y is equal to 432. And if I multiply this equation by -1, I'll have -3x minus 2y equals -216. And add those together, I'll have 4y is equal to 216, and if I divide 4 into 216, I find out that y is equal to 54, and that's a rate, and my distance was in kilometers and my time was in hours. So the units for y would be 54 kilometers per hour. And then I can substitute back into either this equation or the 3x plus 2y equals 16, and put in the 54 that I just found, and find out that x is equal to 36 kilometers per hour. And if you put those numbers back into the description up here, you'll find out that that is indeed what happens. If you take 36 times 3, you'll get 108, and if you take 2 times 54, in the first scenario, you'll get 108. 108 plus 108 is 216. Everything works. Everything fits what we analyzed in our equations. The same thing would happen if you put the 36 in here for the x and the 54 for the y. You get different values. They still add up to 216.